Okay, so today's video is going to be on a review of kinematics and laws of motion. So to get things started, we're going to be chatting about some graphs. So if we are looking at a displacement time, a velocity time, and an acceleration time graph, and let's say we had an object that took a path like so on its position time graph, and we were asked to draw the velocity time acceleration time. Well, since we know that the slope of this graph, which is really a change in position divided by a change in time, is the definition of velocity, what we can do is we could take a look at the velocity, the slope of this graph to get an idea on the velocity. So I'm going to draw in some tangent lines to aid in that diagnostic. So if we were looking at that first line, we see that it's a steep positive velocity, so I'm going to put a dot at a steep positive. Sometime later it's a little bit less velocity, and sometime later when it hits that point it is zero velocity, and then it is increasing its slope in the negative direction. So our velocity time graph would look something like so. And since the slope of your velocity time graph, which is really a change in velocity with respect to time, is the definition of the acceleration, so we could take a look at that slope is a constant negative value, so therefore the acceleration is a constant negative acceleration. Now a couple important points: that the IB uses S for displacement, the AP uses X or Y for your position, both horizontal and vertical. The IB just uses S, and that U represents the initial velocity, so this is the initial velocity, and that V is the final velocity. So it doesn't change the relationships, they're all still there, just slightly different notation. Okay, so things to watch out for, that if you are throwing something up, so let's say we give it an initial velocity, we just throw it straight up. So it goes straight up, comes right back down, we know it stops at the top, we know the acceleration is equal to g, and it's in the downward direction. So what's interesting here is that when the velocity is up, so in other words on its way up, the acceleration is down, we end up seeing that the object slows down, so slow down. When the velocity is zero and the acceleration is still on its way down, we'll see that it begins to change direction, turns. And then when the velocity is down and the acceleration down, we know that it is going to speed up. Okay, so what we can generalize from this is that when the velocity and the acceleration go in opposite directions, we have slowing down, and when the velocity and the acceleration go in the same direction, we have speeding up. Now, what is also interesting to talk about is terminal velocity. Okay, so terminal velocity. So both from a force perspective, but also from a graphical perspective. So we'll get into the forces in just a little bit. But if we look at the graphs, so if we're looking at the position time for terminal velocity, and the velocity time for terminal velocity, and the acceleration time, what I know is that it is going to be speeding up, so it's going to be increasing its slope, and then sometime later, the point at which it reaches that terminal velocity, which we'll speak a little bit more about in a second, that the slope becomes constant, meaning that the velocity becomes constant. So the velocity is increasing, 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 and then it tails off to a constant value, and then the acceleration is at a constant negative 9.1, and then it decreases to 0 sometime later. So now, when we're looking at the forces at time t equals 0, then what we have is that there's a downward force of gravity. The instant someone jumps out of an airplane, for instance, there's a downward force of gravity, and that is the only force acting on you at the instant you step out of that the airplane. Sometime later, so some time later, you have some drag force acting on you. Okay, we're not quite yet at the terminal velocity, but we still have the same downward force of gravity, but that drag force is increasing as you're increasing your velocity. And then sometime later, what we see is that drag force has increased to the point at which it balances out the force of gravity. And that is the definition of terminal velocity, when the upward drag force is equal to the downward force of gravity. All right, so we just threw in some force diagrams in there, but it matched with what we were talking about. Let's move on to projectile motion. We have two different scenarios. We have throwing something off of a cliff. And so what is interesting about this is that you give it some initial velocity in the horizontal, so there's some Vx. That Vx stays the same through its entire flight. And the vertical velocity is increasing. So it gets bigger and bigger as time goes on. And the reason being is that if we draw the force diagram, so the free body diagram, at any point in the air is just a downward force of gravity, meaning that there's nothing acting on it horizontally. So therefore, in the x direction, the acceleration is 0. And since the only force that's acting on it is the force of gravity in the vertical, the acceleration in the vertical is the 9.8 meters per second squared. And it is in the downward direction, so we're going to put that as a negative value. Now, this is true whether you're talking about a horizontally launched projectile, like I drew here, or a ground launched projectile. Okay. Now, what's some things that are interesting is that the mass doesn't make a difference. So that no matter what this mass is, it is still going to go the same exact range, or that is a displacement in the x direction. And so that mass, even though there's a bigger force of gravity, it's going to take more force to accelerate a larger mass, so we have the same acceleration. Okay, so when we're looking at a ground launch projectile, same setup, x and y, and we can make the same assumptions about the acceleration. The other thing that I didn't mention before is that once you find time in one direction, you could apply that time in either direction, because time is a scalar, not a vector. So we're able to separate it into, or put it in both of those columns. Now, we know that the only difference here is that there is an initial velocity in the vertical direction. Now, a couple things that's important to note out, that 45 degrees will give us a maximum range, and 90 degrees will give us a max height and end time in the air. Okay, if I throw something straight up, it's going to go the highest. It's also going to spend the most time in the air. So some more force diagrams. So let's get into forces on ramps. We have a downward force of gravity. We have a reaction force from the surface that we call the normal force. And let's say this block is just sitting there. So there must also be some frictional force. So what we could do is we could break that weight into a perpendicular component and a parallel component. And it turns out, and we could do a little bit of geometry to prove this, that angle is the same as that angle. So we can use that triangle there to figure out the relationships between the weight, the mg, and the weight parallel and perpendicular. So the parallel component is going to be the sine function times the weight, and sine of the angle times the weight. And the perpendicular component is going to be the cosine times the weight. And so if this is in static equilibrium, what we can say about the forces is that that force and that force are the same, and that force and that force are the same. Now, very few times will the weight perpendicular and the normal force not be equal, but the weight parallel and the force of friction, or if there's some other applied force, let's say that there's some pulley hanging over the edge here, and we have some block, and it's hooked up to some other block. Okay, then we have a couple different more forces to throw into the picture on either one, but there still is this weight parallel. Okay, and that's still going to always be equal to the mg sine theta. Okay, and the last thing that we're just going to chat about a little bit is an elevator. So you're standing in an elevator on a scale, and the elevator's at rest. Or let's even say that the elevator's moving at a constant velocity. As long as there is no acceleration, those two forces are the same. Okay, so this is with an A equal to 0. Let's say the acceleration is up. Okay, well, all that means is that there's got to be a larger force in the upward direction. And since the normal force is in the upward direction, there is a greater normal force. And then let's say the acceleration's down. Then that means that there's got to be a bigger force in the downward direction. But this force of gravity is calculated by m times g. And since the mass of you and the gravitational field strength of the Earth hasn't changed, we still have the same force of gravity. So you might be thinking, how can we get a net force in the downward direction? It's a decrease in the normal force. So the scale reading here is going to be equal to your weight initially when we have an acceleration of 0. The scale reading is going to be greater than your weight when you're accelerating upward, and the scale reading is going to be smaller than your weight when we're accelerating downward. Okay, now just one last thing to point out, that an acceleration up can be speeding up in the upward direction, but it also can be, it can also be when we are moving down. So we're moving in the downward direction. Let me just change the color here. We are moving down, so our velocity is down and our acceleration's up, so we can be moving in the downward direction and slowing down and still have an upward acceleration, meaning that in this scenario your scale reading will be larger. And an acceleration down can be us moving up, so our velocity is up and then our acceleration's down. So this is like moving from the first floor to the second floor, but slowing down at the top part. Okay, so there's more than one way to just accelerate in the downward direction. There's more than one way to accelerate in the upward direction. The speeding up in either case is obvious. I think the slowing down is not so obvious. So I hope this helped. I know I went very quickly. Pause, rewind, think about it, whatever you have to do, and come to class with some questions. All right, thanks for listening. Bye-bye.